Welcome to session 7 of LLM Engineering Cohort 3. We are talking fine-tuning today. And fine-tuning is a really big topic. This is something that a lot of things are kind of fine-tuning, as we'll hear as we get closer and closer to the LLM edge out on the frontier. As we get to things like distillation and merging and alignment, we're going to hear more and more like these are kind of fine-tuning, maybe even finer fine-tuning. So today we're going to kind of cover the core aspects that you need to know about fine-tuning. Supervised fine-tuning, let's say. As you guys know, we're on a mission to create the world's leading community for people who want to build, ship, and share production LLM applications. I've seen some folks out there shipping and sharing this week. Just quick shout out to Nile. I mean, bro, you are holding this cohort up single-handedly in the cohort channels. Way to go. If you guys want to hear more about what's going on in the community and you don't read our newsletter very, very closely, you can definitely join us every Monday to hear about all the amazing things going on outside of the cohort in the lounge. This is the public lounge every Monday morning. And I'm pretty excited because we've actually got Christos and a small group of others that are really, really getting serious about accountability towards the end of the year and into 2025. So if you're interested in building your own personal brand and taking it to the next level in 2025, these might be some great guys to connect with. Of course, this week we're talking VLLM, so join us for that. It's a really often misunderstood tool. We'll cover it tomorrow on YouTube. Couple questions that I want to address from the feedback. One is, I wonder who wrote this. Word on the street was that XAI got into some trouble because hardware and software. Wiz, I wonder if you can comment on this. How coupled are hardware and software during the training phase, during the pre-training phase of these big models? If we have GPUs go out, we got to start over?
Yeah, I mean, so yes, unfortunately, this is mitigatable in some fashion, obviously, and it's become something that we've gotten better at over time. So as we move from kind of the naive solutions to like a GPU goes down and training, is unrepairably borked, we kind of got better. But it's extremely coupled to the hardware. Like, Greg, we were watching that wonderful explainer video about the GPU, right? And they're talking about how the warps and the sub warp groups, which is physical locations on the chip, right? So the software we're using is extraordinarily coupled to this very specific hardware. And it's not fault tolerant by itself. We've done a great job to produce more fault tolerant systems. Things like Meta's LLaMa, right, is trained and nodes go down. It doesn't matter. Mosaic has an open source solution for this now. But at the scale that XAI is looking at, which is currently the largest combination of NVIDIA GPUs, you just cannot predict what's going to happen when you have errors at that scale. Yeah,
that's right. That's right. And this idea of distributed training and distributed even fine tuning are starting to become more and more prevalent. And so like that kind of naturally follows from this discussion. If you can distribute it, you're more decentralized. And if stuff goes down, maybe you're more easily able to kind of adapt to that. And then, okay, so I missed the latest tricks novelties, which are used for pre-training, things like synthetic data, mixing data types and formats. Do you recommend any sources or papers where I can find more on the pre-training phase? Anything top of mind for you, Wiz?
Nemotron 4, this is the 340B big model. As well as like the LLaMa papers themselves go quite into detail. So if you read the whole LLaMa family, starting from Meta's original LLaMa all the way to LLaMa 3, they really discuss pre-training ad nauseum. One of the things to keep in mind when we say like tips and tricks is that this is never something that you'll be doing unless you work at these super clusters. We simply don't have the hardware to be operating at this level for pre-training that is kind of pre Superscalar stage, you're just collect more data. The more data you have, the more better. And then you can look at these more efficient things as well. We're going to see more pre-training from kind of scratch with smaller data sets using these fun tricks and switching data structure. One trick that I'll say is like flatly and very bravely, and hopefully continues being true, is like if you want your model to be extremely good at English, you should show it lots of code. For whatever reason, code typically performs performance benchmarks relating to English, assuming because it's mostly English tokens, but in a hyper-structured, hyper-specific order. So yeah, if you want your model to be really good at producing English language, you should show it some code.
Classic. Yeah. And then we will actually get into, as part of our story today, some of the LLaMa, early LLaMa papers, but this is like the meta paper from just a little while ago, sort of the meta paper from Meta on the entire herd of LLaMa models. So that's one that you could definitely jump into. Okay, great questions. And then Wiz, you seem to be off site right now. I have a question for you. I believe you're in Vancouver, right? What are you doing in Vancouver right now? And I'm feeling a little FOMO not being there with you. What am I missing?
Yeah, so today was the first expo day of NeurIPS, which is the big natural language, now kind of just general AI conference. It's being held in my home country of Vancouver. So this is a city in British Columbia in Canada. So today was kind of a lot of expos. There were some oral sessions that they were talking about some stuff that's kind of cool. I think coolness kind of gets accelerated from first day and on. But I did have the chance to listen to a few awesome talks. One thing that I want to stress is that even these talks still go through what transformer is, right? Like we're at the absolute edge of research here, and people still are it's not assumed that everybody knows every architectural detail. I think it's very interesting the level of accessibility that there is in the day one sessions. A lot of the stuff you guys would be able to understand what's happening because we've already been through the guts of the transformer, right? I have noticed the picture 4 times total now. So
stuff like this, stuff like this is what they're talking about. Is that what you're saying?
stuff like
Yeah.
all kinds of fun stuff.
Yeah. Okay.
Yeah, reasoning, evaluation is a word that gets said a lot, and decoding. Actually, there was a session today, which I'll link to some resources to in the Discord, that was about surely just using an algorithm as basic as greedy or sampling for decoding which token should come next isn't the pinnacle of decoding. So there was some interesting thought about that as well today.
Nice. And I did notice that the NeurIPS 2024 Test of Time Paper Awards went out to, one of these was from 2014 when Ilya Sutskever was at Google. And look at this, sequence to sequence learning with LSTMs. It looks a lot like what we just talked about. And I bet you guys could understand what's really going on in that paper. The other one, sort of GANs from Goodfellow, maybe a little bit less, but that's also an absolute classic. So very, very cool. Thanks for the update on NeurIPS.
Let's just be very clear. Allow me to fire shade. GANs did not stand the test of time at all. So anyway, we can move on.
That's right. But that book that he wrote on the back of that thing was, a true legendary deep learning text, as you guys know. Okay, let's kick it off for the day, guys. It's time to get into fine-tuning. What happened to my slide here? Okay, it's time to get into fine-tuning. That's what we're doing. We're not doing pre-training. Okay, so with today, what we want to do is we want to kind of make sure that we just go through a couple of things. We want to make sure today that we're covering fine-tuning, but we're picking up the threads of the story that we've been spinning so far in this cohort. We're going to cover the primary fine-tuning method called LoRA, or low rank adaptation, in some depth as well. And then we're going to kind of show you the way to actually do this. So whereas in perhaps the AI engineering bootcamp that we teach, we'd focus a lot more in on the tactics here and specific aspects of what goes into SFT with PEFT-QLoRA. We're going to really focus here on telling a little bit of the history, a little bit of background of fine-tuning and how this kind of came about. That'll give us some nice context to sit with, and then we can go ahead and get confused about things like quantization and supervised fine-tuning. Okay. Fine-tuning. This is just teaching the LLM how to act. That's all it is. We talked in session 1 about the Shoggoth. We talked about how really this kind of big, messy, huge monster has to then be kind of aligned. We got to kind of fine tune that thing. We got to put the human face on it so it acts kind of like us. And then we can really dial it in and make it happy and not do any harm at all with things like RLHF that we'll talk about next time. Now, when we think about fine tuning, we want to think about this being kind of a supervised thing. And we talked about that a little bit already, because we're generating a supervised data set as we go through the kind of the pre-training process. Now, this supervised approach is just like any classic supervised approach. You know, we talked about semi-supervised sequence learning as kind of forming the basis of unsupervised pre-training last time. But again, we want to sort of see the underlying patterns at play here between all these things. Whether we're talking training or fine-tuning or alignment, whether it's pre-training or post-training, really, we are trying to make sure that the logits and the targets are close, that we're predicting what we thought we were going to predict during training. So this loss function idea doesn't go anywhere, whether we pre-train, whether we fine-tune, whether we align. And remember, we talked about this pre-training thing. It's awfully expensive, tens of thousands of GPUs, perhaps more than that now if you follow XAI, and training for months at a time. And we also saw that there's this post-training phase. So this is sort of where we are when we're talking about fine-tuning. There's this kind of post-training that helps us to sort of really align more with humans, and generally is going to leverage human feedback in some form. And as we heard from the Anthropic CEO, that phase is getting larger and larger all the time, perhaps more and more challenging, less exact. And we also saw that some of the leading small language models that are now 70 billion parameters, they've got a lot of things associated with them. And we're in this sort of step of fine-tuning. So if we take the big LLaMa 3 model, we distill it, then we fine-tune a few others, align a different one, and merge them all into something like Supernova, which we'll sort of get back to in the last session. What's really going on with these little two that we fine-tuned over here? And just for fun, because it just came out the other day, what in the world is reinforcement fine-tuning? One of OpenAI's 12 days this year, dropping this little thing. By the end of this week, we're going to be able to really kind of grok what's going on. We're going to be able to really see through some of the noise. We're going to be able to understand that this is all kind of the same thing, and that ultimately this is really just kind of teaching the LLM how we want it to act. So the first idea I want to introduce is this idea of the spectrum. As we go from prompting into fine-tuning, we're sort of optimizing the LLM along this dimension, this sort of task-specific dimension. This spectrum of task specificity is kind of asking, like, how much data, how many examples do I need to do well on a specific task using any sort of given large language model? And a zero-shot task would be something like translate English to French, just the instruction. Cheese, we're looking for fromage here. Okay, so, and then one shot, it's one example. Here's an example. few shot. Here's a couple examples. And if I go one shot, two shot, few shot, 100 shot, 1,000 shot, million shot, eventually I get to this point where I can no longer kind of put this all in context. I have to kind of move back into a traditional fine-tuning domain. And that kind of makes sense intuitively because we kind of went the opposite way when we were developing these models, but only for the first part. Remember, we talked about GPT, and they said, well, when we pair supervised learning, aka fine-tuning, with unsupervised pre-training, we do very well. In fact, we can get this huge, awesome jump in performance very, very early on if we add supervised fine-tuning on top of unsupervised pre-training. And so we do the general pre-training, and then we do the task-specific fine-tuning. Note that each line is associated with a different task. So that task specificity, that smaller amount of data, that's what we need when we're talking about fine-tuning. And we talked about how GPT used these underlying ideas like ULM fit and semi-supervised sequence learning, the sentiment neuron as well. And it turns out that GPT was actually trained on a kind of a very small amount of data. It was trained on the books corpus data set. This is a data set with over 7,000 books. Okay, so a lot of books. And books are cool because they have sort of long range and short range ideas that are connected. So these sort of long stretches of contiguous text allow us to kind of learn this long range information. And it did pretty well. And, 12 blocks, 512 token sequence, we kind of remember all that. And these attention blocks kind of correspond to attention layers, one in each block. And of course, each of the layers have many heads. And, the GPT architecture was kind of like this. We had 4.5 gigs of text, 117 million parameters, 12 layers, 12 heads. And they said, well, we need more compute, always need more compute. We're a little bit worried about the bias this thing's showing towards some things. And really, the generalization is still not fantastic. So can we do better? Can we get better language models? GPT-2 comes along, 2019, yes. GPT-2 showed us that language models began to learn tasks without explicit supervision. Weird. Okay, so now we actually don't even need it anymore. This was not just the books corpus data set. Now, this was actually the web text data set. So 10 times more text than GPT. And we kind of this 1.5 billion parameters versus 117 million, 10 times more parameters. So in this case, the data, they looked at Common Crawl, which we won't get into in great detail, but Common Crawl is this massive data set, and it's this great open source project to sort of crawl the internet for all of the text. But as they point out in this paper, and as you'll notice if you study the data sets of many models that have been trained since, there's a lot of cleaning that has to be done when you do this, and you leverage a data set like Common Crawl. So instead, they said, we're going to build something else. We're going to build the web text data set, and we're going to create this web scrape that's mostly going to be kind of based on Reddit. Okay, so at least 3 karma. You can have lots and lots of karma, but we're sort of saying, okay, we have at least some threshold of quality here. And so this can be sort of, something was interesting, something was educational, something was funny. These are sort of points that people get for their contribution to the community. And it worked pretty well. It worked so well that they were like, without any explicit supervision, we get really good results. Like, we don't even need fine-tuning. We really just need to prompt this thing. And so, at that point, it was kind of like, oh, I guess we don't need fine-tuning anymore. Cool. 48 layers. It wasn't clear exactly how many heads from the paper. 1.5 billion parameters, 40 gigs of text, 10xing. And they built a number of different sized stacks here. Now, a year later, year and a half later, really, almost 2, GPT-3 comes out May 2020, and they're like, okay, actually, we can keep scaling this up. We keep not needing fine-tuning. Now we're at 96 layers and 96 heads, and we're doing all sorts of permutations on these with different sizes, from 1.7 billion to 175 billion, from 50 to 500. So we 10x'd again, and they're like, man, these things are really good. And since we don't, as humans, require large supervised data sets to learn how to do new stuff, it makes sense that these models don't really require it either. We're very good at following instructions. In fact, that's the #1 rule of prompt engineering, or maybe of working with other people, is giving clear and specific instructions. And there are other rules to prompt engineering that are beyond the scope of a talk on fine-tuning. The core of the GPT-3 paper, though, was really about this idea of in-context learning, what we come to know kind of as prompt engineering. Zero-shot instruction only, not so good, but once we give it just one example, 2, 3, 4, all the way up to 30 plus examples, we do better and better and better. And of course, this improves with pre-training. It improves with the number of parameters in the model. Now, at the time, it was pretty cool because there was a data set back at the time called GLUE, the General Language Understanding Evaluation Benchmark. It was a bunch of different benchmarks. And then they were like, oh, GLUE got crushed. We need to make super glue. And then they were like, oh, man, that got crushed too. And it's been going on for years like this with benchmarks. But what's super interesting is you can kind of see the same pattern from this paper as we saw from the original GPT model. That is, we get this kind of unsupervised pre-training vibe. And then if we just use just 1 or 2 examples, boom, we're just smashing it. Now, we're smashing it as we go from this 0 shot to 1 shot, 2 shot, 3 shot. And remember, 0 shot is instruction only. But we're giving it a very specific instruction. We're giving it maybe 1, maybe 2, maybe 10, maybe 20, maybe 50 examples. And then maybe if we have 10,000 examples, we have to do fine-tuning anyways. And maybe if we want it to be really good, not just at one task, but at many tasks, we need lots of examples. So it kind of led to the question for them to ask of like, well, how can we get better at following instructions in general? And this led to a lot of work they did over the next couple of years, all of which led up to GPT 3.5, if you guys remember that, which was kind of like what came out of Instruct GPT. And unsurprisingly, you'll see that Instruct GPT is better at GPT-3, better than GPT-3 at following instructions. Let's go. Like this one. Why aren't birds real? Instruct GPT with the on-point answer. Birds are not real because they are not made of flesh and blood. They're made of feathers, bones, and organs. Astute point, Instruct GPT. Thank you for that. Little less chaotic than GPT-3. Again, these were early days. Another example, explain the moon landing to a 6-year-old in a few sentences. People went to the moon and they took pictures of what they saw and sent them back to Earth so we could all see them. All right. This is sounding more aligned, okay, but the big thing here with this paper was the language modeling that they were using, the predicting of the next token, was different, quite different from the idea of follow the user's instructions, be helpful, and do it safely. And this is where this word is introduced that we've come to know so well, misaligned with our expectations. We need to align these things to our expectations, especially if we're going to deploy these kinds of models in hundreds of applications. Oh man, we got to do something. And so Instruct GPT said, we're going to figure out a way to align language models to follow instructions better. And it turns out that they did a really good job at this. How'd they do it? Well, they did some fine tuning with human feedback. Let's check this out. Starting with a set of labeler written prompts. That means humans wrote the prompts. We collect a data set of labeler demonstrations. What does that mean? It means humans wrote the output response to the instruction. So we have human written instruction, human written response. Beautiful data set. And what did they do? Well, they did instruct tuning. Haha. What's that? Well, it's just fine tuning, but with an instruction data set. So that when we kind of give general instructions, not just one super specific task, we can actually be more flexibly able to handle those instructions and produce a proper output. This was, in hindsight, rather quickly also adopted by Meta in their large language model Meta AI models, the LLaMa models. And you'll notice if you read the LLaMa papers that they were out there comparing to all of the open models, but also comparing to GPT-3 at the time and other instruction tuned models. This is where this starts to gain some steam, this idea of instruction tuning. And instruction fine-tuning is just fine-tuning on instructions. Okay, it's always been that. Whether you're talking to GPT and OpenAI or whether you're talking about LLaMa and Meta. Now, importantly for us today, pretty much all of what we've been talking about so far, we can assume was what we would call today full fine-tuning. And what full fine-tuning is full fine-tuning is where we fine-tune all of the weights and we do it all in full precision. Now, this is not smart fine-tuning. This is like level 1 fine-tuning. And there were a lot of papers written at that time like, hey, man, I'm worried about like if we need all these different fine-tuned models, we're going to kind of explode the amount of compute and memory we need. It's going to be crazy. We got to find smart ways to get around this. And like there's things that indicate to us that like some weights matter more than others. Maybe we don't need to train all of them. Like literally, if we look inside the transformer, as we know, there's weights everywhere. There's like weights in attention, there's weights in the layer, there's weights in the feed. Like, what should we be training exactly? So rather than level 1 fine-tuning, can we do something that's a little bit smarter? Can we do some smart fine-tuning? Something where we could maybe like make the weights a little bit smaller, small as we could make them without changing the output. And then maybe we don't have to consider all of the weights when we're fine-tuning. And this gets us into our first concept that we're gonna have to work to Grok, which is quantization. You see, the problem is we have these big models and they're like so big, we can't even use them. So the big idea behind quantization is we take our big bucket of weights and we represent them with smaller numbers. Numbers meaning ones that we can use for computation as we run through attention calculations and the like. So you can kind of think about this. It's a rough approximation where we're just kind of playing the significant figures game here. How many are we going to use for our calculations? Because now we're trying to optimize. And to optimize anything, we need constraints. Our constraint is our GPUs. It's how much model we can fit on them and how quickly we can move through a process like fine-tuning. And this is our constraint when it comes to LLMs in general, whether we're doing inference, which is quite important, but now we're talking about training, we're talking about tuning, we're talking about this part of the paradigm. And this idea of like being smart during training, during the training phase, with the way we manage the size of our models, gives way ultimately to, when you start building applications with these, being smart after you're done training, and you can kind of lock things in. So ultimately, this is a compression, this idea of quantization. We are going to lose information with this. And, the idea is we don't want to lose so much information that it feels like the thing's different anymore. We just want to leverage enough of our model so that we change it to adapt it to the behavior that we want. And in order to do that, we need to do a couple things first. One is we need to get the model into a place where we can actually then load it into our GPU and do some training on it. So we have to download it. And as you guys, I think, noticed last time, this can be a little bit of a pain, especially with very big models. So we're typically downloading in full precision, typically downloading so that these model weights are represented by very large, from a bit width perspective, numbers. And so we need to sort of configure libraries so we can set these things up. We need to then get our model down into, in our case, our Google Colab notebook, so that we can load it up into the GPU and leverage the GPU memory. And our model today is LLaMa 3.1 8B instruct. You might notice -instruct indicates it has been instruction fine-tuned. What we're going to do in the first breakout room is we're just going to get set up. And then before the second breakout room, we're going to talk more and more about how exactly the fine-tuning is happening, what's going on, and what we're going to try to fine-tune this thing to do today. Wiz, go ahead and show them how to get set up with LLaMa 3.1 8B instruct, quantized this time.
Oh, okay, good. Yes. Okay, so first of all, this is in the repo. So if you want to just head to the repo, you can go to session 7, which is fine-tuning. You're going to find the first notebook and the second notebook. Also added a hard mode. Has absolutely no instructions other than the task for the brave among you. But what we're going to do is we're going to load the model today. And Greg mentioned it. I think it's worth repeating. So the model is huge, right, by default. So you can actually calculate trivially how huge. So we have an 8 billion parameter model. Each of those parameters is typically stored in a full precision number, which is a 32-bit floating point number. So each parameter is worth 32 bits. So we have 8 billion times 32 bits, right? So the model is huge. Like on disk, it's huge. And obviously, even when we connect to our A100 instance in Colab, which is the largest compute available to us in Colab, you'll see that it's not at all, the math doesn't check out. So if we look at this, you can see we have a total of 40 gigabytes of GPU RAM. So we need to do something, and that something is called quantization. And so let's get into it. Okay. So first things first, we have a discussion question, which is just, why is this a good model to use for a translation task? It's, it's not like a secret answer or anything. Just have a discussion amongst yourselves while you wait for the model to load, because it's going to take a while to download all the checkpoints. And then we have an overview of PEFT-QLoRA, which we're going to get more into in the second breakout room. You got to download a bunch of libraries, classic. You'll notice our transformers is coming back. We're adding this PEFT-QLoRA lib thing. We're going to always add accelerate. This is just to make our lives easier. And then data sets and bits and bytes are some new friends. So the first thing we'll do is just make sure we're in a CUDA enabled instance. If this says false, you have to go to your runtime, change the type, and make sure you're choosing one with the GPU. I would most prefer you to choose the A100, though you can use the T4 if you change a few of the hyperparameters that we'll talk about later in the notebook. Okay, and then we're going to get a bunch of stuff, including bits and bytes and transformers. They're going to start loading the model. Now, one thing that I always have to remember to mention is that we actually load the model in full precision. So we download it in full precision, which means that we have access to the 32-bit weights, or in some cases now, in most cases, I would say B-float 16 weights or half precision, depending on the model producer, which is kind of where part of the process of moving in the field is understanding that maybe 32 bits not necessary all the time. But what we're going to do is we're going to actually download the full weights from the Hugging Face hub, and then we're going to quantize them when we load them onto our GPU. So we're not going to quantize them before they're actually loaded into the GPU. This is important for a number of reasons, but mostly we want to make sure that we have access to full precision should we need it. So quantization is a very long way of saying make big things small. The idea is we want to take this 32-bit representation of a number and express it in much fewer bits, hopefully as low as 4 bits. And so there's going to be some necessary information loss if we go from 32 bits to 4 bits, but there's a lot of clever math that we can exploit about the transformer in order to lose as little information as possible. So right now, we're just going to talk about bits and bytes. Bits and bytes is kind of like the stock quantization. It's like the most traditional form of quantization. We apply it post-training. We can apply it whenever we want. We can apply it to whatever we want. This is different from methods where we might have to do some additional work in order to quantize, like some we've talked about in previous events. But for this actual bits and bytes, implementation, it's very straightforward. We're going to use this k-bit training. K-bit is just k, or k is some number, always a power of 2 bit training. So today we're going to be doing 4-bit training. So we're going to use this blockwise k-bit quantization, which is like a bunch of words. But the most important, words in this sentence are the ones that say blockwise. So if you think about the way that we express the actual information in the model, it's always in these weights, right? We've talked about them a lot. And the weight is just a number, right? So what we found out through research is that most of the weights in a large language model are actually normally distributed. So what this means is that they are clustered around a certain value, and there's lots of them near that value, and there's not so many as we move away from that value. And so we can exploit this in order to do this blockwise k-bit quantization, which is to say we can think of the weights in sets or blocks, and then for each block, we're going to quantize, and we're going to doubly quantize. But that's left to you to talk about in a question. The basic idea is that if you think about a normal distribution, a bell curve, right? What we're going to do is we're going to record where the mean is. We're going to record where that most popular value is for each block. And then we're going to say, instead of storing numbers that indicate the actual value that we're looking for, we're going to instead store the relative position of those numbers, or in which standard deviation they live when compared to the mean. So we take the peak, and then instead of storing each of those numbers in that normal distribution, we instead just say, okay, well, it's like 1 standard deviation to the left, 1 standard deviation to the right. And this is, lossy for sure, but it's not that lossy. And it turns out that when you have 8 billion of something, the loss works out in the math. So we have some language about that in the notebook. It's all great to talk about, like the theory, right, of quantization. It's always fun. It's one of my favorite topics. But we have to know how to do it. And so how we do it is with bits and bytes config. We have our load in 4-bit equal to true. We're going to use this quant type of NF4. This is Tim Detmer's almost information theory efficient data type. So this is almost theoretically the smallest we can get these particular set of numbers. Technically, some research came out that said, Tim, you're close, but not quite. But NF4 is the data type we're going to use. if you look into the QLoRA paper, which you're able to do, there's links to it in the actual notebook, you'll see that NF4 is in fact definitely not a number. It's a collection of numbers. And what we do is we represent where we are in that collection of numbers, and that's what takes 4 bits. Again, we're kind of finding these ways to like cheat around how we're storing information. So just to really hammer that home, I'm going to commit a cardinal sin, and I'm going to apologize deeply to Greg. But the idea is that I'll just scroll a lot, which I know is always the most fun, and we'll look at the NF4. So this is what NF4 is actually. And you'll notice it's nonsensical, and it's also a list. But you'll know the assumed monkey will be able to count the items in the list and say, hey, I bet if we had 4 bits, we can represent every element in that list. And indeed you can. And so we basically have a lookup table to these values, and these values describe that normal distribution, right? So this is the way that we can quantize. You're going to also notice that we have a number of operations which are actually going to be stored in full precision, like these numbers can't be represented in 4 bits. But we only have to store them 1 time versus 8 billion times. So the savings hopefully are clear. Okay, so that's our NF4 quant type. It's just a big list of normally distributed floats. And then we're going to do this double quant thing. We're not going to get into double quant right now, but it is left to you to discuss. The idea is that if one block is quantized, what if we took a block of blocks? Could we quantize that as well? The answer, of course, is yes. And you can read about how they did that very cleverly in the paper. And then we're going to use a compute D type. Now, this is where you get into a little bit of trouble with Tim Demers' bits and bytes library. So you'll notice that we have this idea of a compute D type. This is because we're not going to do any useful calculations with this weird address or pointer to a different number, right? So as we move through our network, we're actually going to dequantize these numbers into this float 16. We're going to do some computation, and then we're going to requantize them. So effectively, this looks like a rippling effect as we move through the network, where for every computation, we're going to dequantize, and then we're going to subsequently requantize. So we only have one layer of the model, or one active part of the model that's loaded in half precision at a time, as opposed to the whole thing. So it's still a lot of memory savings. However, you probably think to yourself, well, is it free to de and requantize? And the answer is absolutely not. This does introduce some latency overhead when we're doing inference. Don't care so much about training. It does slow training down a little bit though, but definitely for inference, this is a little bit of a beater. So, and then the question to you: what happens in the double quantized step? But this is it. Like, this is all of the stuff we talked about and the crazy number I showed you guys. In Python, right? This is all we've got to do, and then it just works. So, thanks, Transformers. We're going to go ahead and then load the actual model. And we've already seen this part. It's exactly the same as before. We're just kind of going deeper on that B&B config. If you don't have your Meta LLaMa license, if you haven't signed up properly for it, you can use the new research model, but really, you should really sign up for this. We're going to keep using it in every notebook because LLaMa likes to come up with new models every 15 minutes or so. And then we have our tokenizer. Each model has its own tokenizer, or each family of models has its own tokenizer. Then we're going to do this stuff. I'm not going to spend a lot of time on this. So this is a bonus question. It's not even for like marks or whatever. But you think about why we're doing this pre-processing for a tokenizer. It is important, and it might help shape how you think about it. We'll touch on this a little bit more once we get into the second walkthrough. But right now, just know that we have to do these pre-processing steps for our tokenizer for training, because it's going to help it learn better. And so that's what we're talking about. That's what you guys are doing in the first breakout room. I'd suggest you run the cells to get to the part where you're loading the model, and then go up and try to answer the questions just to most efficiently use your time. All right.
So we are back, and we're talking low rank adaptation. We're talking LoRA. And the important thing to understand about LoRA is that anytime you do fine tuning, you're probably doing LoRA, okay? Anytime anybody's doing fine tuning, they're probably doing LoRA, okay? What's LoRA? Well, low rank and adaptation. That's what we need to sort of get a handle on. Look at this. As we pre-train larger models, full fine-tuning, which retrains all model parameters, becomes less feasible, as we know. So we propose LoRA, low rank adaptation, which freezes the pre-trained model weights, freezes all weights, bold, injects a trainable rank decomposition set of matrices into each layer of the transformer, greatly reducing the number of trainable parameters. That's pretty dope. Now there's some intuition that we can sort of get by looking at where this came from, this idea that updates to the weights have a low intrinsic rank. So, you know, we can sort of imagine that this idea of intrinsic dimensionality. So we're making updates, you know, again, we're fine tuning, okay? We're not pre-training. We're not making very large steps of change all the time. We're just fine tuning. And so when this is the case, we're trying to kind of move, just shift a little bit. We're not trying to sort of move all the way over here. And as a result, we can be a little bit more aggressive with some of our updating policies. And we can be a little bit more confident in the fact that we're not going to change everything all at once. So this idea of this intrinsic dimension of these updates, when I'm doing this reparameterization, this is going to be the kind of key assumption that we're leveraging here. You probably remember from matrix algebra and from, you know, things like principal component analysis, that we can take all these dimensions and we can kind of smush them down into a couple of specific features. This is kind of the same idea here. Which dimensions matter the most? Which features matter the most that we're learning within our network? And we really only care about those. And then we use some special matrix math stuff that you probably remember from whenever you studied this, whether in school or on the internet. And, you know, we kind of say, all right, well, we're going to use this little bit of fancy matrix math. We're going to shove these things in. We're going to plug them in like the adapters they are. And we're going to just train those. Now, this is really, really cool. Now, this obviously has a number of advantages, and you can do lots of things with these adapters. This little visualization, this is from Apple talking about their 3 billion parameter on-device LLM. Guess what it's using? Well, of course, LoRA. So the thing from a business perspective that's so cool here is that we can train all these different adapters. We can just lay them out. We can decide which ones we want to plug in. And the best thing is we can decide which one we want to plug in at inference time. So we get no additional inference latency by applying this method. So this is not the only efficient fine-tuning method, but man, is it the most important one. Wiz, you've talked deeply about this method on your YouTube channel originally, and obviously since, as we've been teaching this for years at this point. What's the quickest way for you to explain LoRA to people as they look at one of these classic charts?
Yeah. So basically, the model has weights in a big matrix, and big matrix multiplication is very expensive because 1,000, like what is it, like 10 by 10 is 100, right? But 10 times 1 is only 10, right? So and then 10 times, or 1 times 10 is only 10. So if we plus them up, it's only 20 versus 100. This is the idea of LoRA. The other thing is, like, most of the weights of the model just don't matter. This is the beauty of LLMs. We exploit this constantly once we learned it. But a lot of these weights just mean nothing. They're extremely collinear. They can just be, we can literally just ignore them, up to the point of literally setting 99% of them to 0, which this is much less drastic than, right? So because of this, we can represent them with these very small matrices to do our specific tasks. And this is the important piece, right? To do our specific tasks. The other thing to recognize with LoRA is like the pre-trained weights never go away. They stay there. They stay there in their full glory the whole time. And so we're just able to build these little nudges on top of that. We're going to talk in the notebook a little bit more in depth about that, but simplest way I can say it is that most weights in the model don't matter. And so why would we use big matrix when small matrix would do?
And so when we talk about this idea that some weights contribute more, but we have kind of these weights everywhere, there's like 8 billion of these things. Which ones are we injecting the matrix into? Are we injecting it into this layer norm? Are we injecting it into this feed forward? I think intuitively it makes sense that we would inject it into the attention layer, right?
I mean, definitely you got to inject it at the attention layer. But also, why not every other linear layer, right? Like,
Why not?
why not every matrix in the dang model, right? Like, if it's big enough and follows certain properties and we feel certain ways about it, which we'll talk about again in the notebook. But yeah, I mean, the first time we tried this, we said, well, let's just do the attention mechanism. That makes sense, right? In fact, let's just do Q and K. Let's not even do V, right? We need to, the intuition is we need to preserve V because V is our value, right? And that's going to be what drives a lot of this. And we can maybe just, but then we learned that just literally blanket apply it to the whole thing.
What a classic learning from LLMs. Just do it with the whole thing. Just shove more in and see what happens. Okay, awesome. So that's LoRA in a nutshell, guys. And the next thing that we need to talk about real quick is as we go and we try to fine tune, what we're doing is we're trying to teach the LLM again how to behave, how to act. And when we download for storage, that's in full precision, 32-bit representation. As was mentioned, we're going to load it onto the GPU in a quantized 4-bit representation. When we do fine-tuning then, we've loaded it onto the GPU, it's in 4-bit. We have access to the full precision 32-bit. We're going to have to do calculations during fine-tuning. That's sort of a training-specific discussion you can have more in your breakout room. And when we do quantized low-rank adaptation, or QLoRA, what we're doing is we're training the model using this 4-bit representation, but then we sort of dequantize, or we sort of upcast these things back to 16-bit when we need to do a calculation, and then we sort of bring them back down to 4-bit and store them back on the GPU. So there's this real nice sort of wave of quantization and dequantization happening when we're doing the fine-tuning. Very cool. But what are we fine-tuning exactly? Well, there's 3 primary things that we're going to be focused on when we pick out a supervised fine-tuning tool. Number 1, we're going to be aimed at a specific task. Hopefully you're feeling duh on that one. Number 2, we might be constraining the input and the output schema, the format of the response or of the input. And number 3, we might be trying to kind of teach it this new domain or language of words that it wasn't really trained on. So when we think about task training, this could be anything, any task, summaries, QA, sentiment analysis, etc. All the tasks, they're all fine. This is like, why would you actually need fine tuning? Well, you might be able to prompt your way to this. But if you have 10,000 samples, maybe you just want to do some fine tuning, especially if you're going to run it a bunch of times, because each time you run inference, you're going to have to run all those samples. As we talk about constraining the IO schema, this is more like, what do we want to have come out? Do we want always to be able to call a function or to use JSON? We've talked about that. Do we want to always be able to write a haiku, write a LinkedIn post? Or do we want to only use our input and we want to be able to select one of the products that's in our product portfolio and then say, create me a LinkedIn message in the CEO's voice? This is the kind of thing that we can start to design our application the way our user interfaces with it by fine-tuning it, which is really, really cool. And again, you can prompt your way into this for sure as you start building these applications. And finally, we're going to do language training, training the interpretation of new words. Let's not say the understanding, let's say the interpretation, because we're sort of rewiring So you might do this for very specific legal or medical language, or you might do it like what we're going to do it for today, to try to fine tune to understand Gen Z a little bit better. So we took some English Gen Z pairs of data, and we're going to fine tune this instruct-tuned version. This is the best practice today. Always pull the instruct-tuned version off the shelf because it's already been fine-tuned for instruction following. So it's going to listen to us quite well. We found this Gen Z translation data set. So we're going to take English Gen Z data set, data points, and we're going to see now how we can go using LoRA. We can go from having 41 billion trainable parameters. I believe this is right. I think I missed a comma here. It's less than 1% of the parameters
sub 1%.
here.
That's
sub
right.
1%. So we are talking 41 million of 4 billion. That's what we're talking. So 0.9% of the parameters. And with just 0.9%, we can get incredible results for sounding just like Gen Z. This is the magic of fine tuning. This is what we're going to see. Wiz, throw a little spice on this thing. And this is a heck of a notebook. So buckle up, guys. We'll be in it for about 15 minutes straight here. Over to you, Wiz, quantization, fine tuning with PEFT-QLoRA.
Oh, let's go. Okay, so we've loaded the model. Very cool. We've answered some sweet questions. Very cool. We've lined up these layers. Very cool. And now we're ready to get some data. So we need some data, obviously, to do some training on. And the way that we do this training is pretty straightforward. We simply show the model examples over and over again. So we have a number of different data sets that we could use. We have some code contests, we have some Farsi instruct, we have some Opus books, or we've got this very on theme, on brand makerspace style Gen Z translation task, which is of course the one we're going to do. So the simplest thing to consider here is that we have the actual translation is going to be, we're using this term very very loosely, let's say, right? This is translation is happening, but it's not like French to English translation, right? The model doesn't care though, so that's what we're going to do. Okay, and translation itself as a term has expanded quite a lot, like translated natural language into code solutions. Lots of fun quirks. In order to get the data set, we're going to use the Hugging Face datasets library, which is available from Hugging Face, and all we have to do is say load dataset. Then we're going to look and see what we have in our training sets. 821 examples. You'll notice that this is very few examples, and that's part of it. We have we're going to split this into train, test, and validation, just so we get a validation set. So we'll have our training set, our test set, and then val. If you're new to yes, no cap 821. If you're new to machine learning generally, validation is kind of like an eval set that we look at during training. So it's not very useful for benchmarking the model's performance or telling us how it did, but it helps us have like a checkpoint to see how well we're doing. So while validation is absolutely leaked into the training process, it's still a useful thing to do. And then of course, a test set, we never show the model until we evaluate. And technically also, depending on how severe you are, this is also leaked into the training set, but we're just gonna live in a world where we don't worry about that. Okay, so the next step is to look at what our data looks like. Our data looks very cool. I like our data. And once we're going on to the next step, we have to do this very fun and interesting process. So we've talked about tokens, right? And what these models have done now is they've introduced very special tokens that have a specific meaning to the model. Now, to us, this looks like beginning of text. To the model, it just looks like 7, or whatever token ID it gets. But the idea is that these tokens are wrapping our prompts. So if you've ever used ChatGPT, you've ever heard the term like system prompt, right? This is where this comes from, where we have these special tokens, and these tokens are included in a very specific format, and they help the model to understand. They act as like little landmarks, right? So this is the start, and then this is the end. And they found that using these special tokens was just incredibly effective at improving how well the model can learn tasks. So we have to use this actual instruction template because of the model that we're using. And so we do. So we have our system header, which is located in this sequence of tokens. So we have our start header ID, then system, and then we have end header ID. And then we have our actual instruction, which is going to be translate this, please. And then we have our user, which is going to be the text. You'll notice this original text. This is not a special token. We could make it a special token if you wanted to, but we're just using it as a kind of extra guidelines. And then we have finally our assistant set of tokens, which is going to be basically the response, including an end token. Now, you'll see in our data that we have just kind of like these sentences, right? So we're going to have to build a function that builds all of this stuff. So we're going to go ahead and do that. And the hard mode is left to you. But for the normal assignment, we're just going to provide it. So this is our instruction prompt template. And it's basically just going to be exactly what we saw above. We have our system headers, then we have our instruction, then we have our user headers, and then we have our original text, which is to be translated, and then we have our assistant headers. Now, when we're doing generation, we actually want to leave this bare, right? We don't want to provide the response for the model. We want to let the model come up with the response. But in the case of training, we do want to provide the response, right? So that's why we have these split into two. You'll see for our prompt, we have include response, which by default is true. It is basically just going to concatenate these two formatable strings with the strings present in our data set. So at the end of each of them, we'll get this kind of thing where we have, you must translate this text. And then we have, let's go to the mall and have fun. And then we have, let's hit up the mall squad. We'll have so much fun together. So this is something to keep in mind when you're building these prompts, right? This stuff is much like to a human, maybe it's kind of like not super sensical. To the LLM is incredibly important because this is how we tap into that instruction tunedness of the model, right? And that's something that we want to focus on really hard in our fine-tuning journeys. We always want to think about fine-tuning from this perspective of we're getting better at some task. If we're not getting better at some task, then we're having a bad time. So what we do is basically we set up this novel task, which is this Gen Z translation task. We show the model many examples. Now, if you've ever used something like ChatGPT and you've seen people or heard people talk about like few shot, which is to say like, hey, just show the model like a bunch of examples and then it will probably be better at the thing you want it to do. This is the extreme of that, right? So we're showing it many examples and we're also allowing it to learn during that process. So basically that's what we do. Then we're going to have a generate response, which is just going to use our model to generate a response. You can see things like we can use this test string to produce let's low-key hit up the mall and get turned up together. And we can see that it's not the same, right? But it's close. So the model by default is actually already not that bad at this task. It's not as good as we want it to be. It's a little silly, but it's doing its best. We try another one. I'm low-key out of space on my phone right now because all the pics and vids are taking up all the room. And then my phone storage is maxed out with all these pics and vids. So again, we get Gen Z language, but it's close. It's not exact. So we're going to fine tune to make it better. So before we can fine tune, because this model is still big, right? Like it's not that big. We made it smaller because of quantization, but when we train the model, now we have to consider like all of these optimizer states and all this other baggage that we have for training, which takes up a lot of room, basically on the GPU. And so this is where LoRA comes in. Now, another thing we have to think about is there are some layers of the model that we actually don't want to quantize. And so this is where we do things like prepare model for k-bit training. This is going to make sure that pieces of our model that should remain in float 32 or higher precision remain there. So one of these is the layer norm, for instance. The layer norm is going to get arbitrarily close to zero. We can't represent that well with our quantization, and so the model, the training will explode basically if we don't keep track of those values, which we really don't want it to. So we just leave them in float 32. This is useful, and we can target specific layers. And luckily for us, layer norm is tiny, so there's no real overhead there. Next, we're going to set up PEFT. PEFT is the best. We have this LoRA config. So we talked about how big matrix, right, split into two smaller matrices. These matrices are going to have this value R for rank, which is basically just going to be one dimension of the matrix. So if we go back to Uni math, right, we think about like what happens if we factorize a matrix, right? Well, we're going to get basically two sub matrices that when we recombine them or factor them together is going to produce the original matrix. This is the same thing we're going to do here. The specific thing about LoRA is that we're going to take, like, if we have an M by N matrix, we're going to get an M by 1 and then a 1 by N sub matrix. So we're going to have these really skinny matrices. That's just the way that it works. It makes the math work. So that's why we do it. You'll notice though that like R can be very low. It can be as low as like what, which is really tiny, or it could be higher, like 64, which is still really tiny. We're dealing with an internal dimension of the model in the 4000s, right? So, but this saves a ton of space because when we're actually doing the computation, again, if we consider just the really simple example of, say, our matrix is 100 by 100, right? That's a very large number versus 1 by 100 or 100 by 1, and then adding them together, much smaller number, right? And the higher we go, the bigger the gap gets. We've all been there. Yes, it's crazy the performance we can get with 64 when compared to 1. There's no fast rule on what rank you should use. It's very dependent on your task and model, but generally you're going to start in like the 8 range and then go from there. Also for fine-tuning, it's basically fine-tuning means LoRA at this point, is how ubiquitous this method is across the industry. So we're going to use a rank of 16 for funsies. We're going to use LoRA dropout of 0.1. It's just a default value for the paper. And we're going to use a LoRA alpha of 32. We don't have to worry too much about this, just a scaling parameter. And then we're going to target all linear layers in our model. And our task type is going to be causal LM, which makes sense because these are causal language models, right? So we basically just pick the task we're doing. Not so bad. Now we're also going to include no bias. Again, just default from the paper. So this is like, again, LoRA, we talk about it, it's these two matrices and we factor them and then we learn on those factored matrices. One thing to keep in mind is while we are learning to build these factored representations, we are combining them back together for the actual computation. So the thing that we're really learning is their combined representation. It's not the individual matrices. So that is literally the weights we're updating. The thing that we're inferring from those is the combined matrices. One other thing you might think to yourself is like, so how does this how does this work, right? The beauty of training or fine-tuning an LLM is we start with some base weight and then we make updates, right, to that weight over time. So through each iteration. Now we could keep recombining our updates into the original matrix, right, and wind up with this initial weight matrix that's been modified many times, right? Or we could like just save all of the actual updates somewhere else, right? So that's what we do with LoRA. We keep the base weights of the model frozen, and we never actually touch those, move those, or do anything. We actually find this delta W or this change in weights which we get through our updates that we can then reapply to the model. There you go. Okay, and then again in code, it's nice and easy. We use get PEFT model with the PEFT config, and it does all the work for us. And yes, we're training less than 1% of the total parameters of the model. Again, when most parameters don't matter, we can do stuff like this. You'll see when we print our model now, it looks a little bit different. We have these LoRA linear 4 bits now. We have these LoRA embedding A and embedding V, LoRA magnitude vectors. So we have this idea of these A and B matrices, which are going to be the sub matrices that we're dealing with. Okay, and you'll see that we have these 4096 by 4096 beasts, and instead, we're gonna go with 16. Not bad. Feeling pretty good about that one. Okay, so now we're actually gonna train the model. This is all like setup, right? So catastrophic forgetting was brought up in chat. Catastrophic forgetting is the idea that like we can train the model and it forgets how to be good at the stuff it was already good at. LoRA is so good at mitigating catastrophic forgetting, right? Because we never touch the base model weights. So if we start to forget, we can just back up a few iterations, change some things around. We always preserve the original model weights. So by nature of LoRA, even if we train the model too much, we just go back to the checkpoint it was and we keep going. LoRA is also extremely lightweight, so we can do that kind of exploration a lot easier. But LoRA is great for catastrophic forgetting. It's perhaps not as good as generalization because we're targeting very specific parts of the model's weights, right? So that's why we say it's task specific, right? Like a translation LoRA adapter makes sense, but like a generalized adapter makes way less sense, right? So we're not going to do instruction tuning as much with LoRA as we'll do specific instruction tunes with LoRA. Though, it really, it depends and all the other stuff, the usual caveats. We won't worry too much about that. We're going to use this new library called SFT, which is from TRL. You love that. SFT just means Supervised Fine-Tuning. Let's go. It's all in the name. So like I was saying, we have this idea of, sentences and then what the response should be. And so what we do is we just show the model that over and over again, over and over again, over and over again. We want it to generate the thing that we told it to, and we don't want it to generate something else. And so we can easily compute the loss there. The actual training args is a big wall of stuff, but it's pretty straightforward. We're going to train a maximum of 100 steps. On each device, we're going to have a batch size of 1. This is just to keep GPU usage down. We're going to do 30 warm-up steps. So remember we talked about last time the idea of learning rate. So learning rate is really important. Warm-up is basically where we ease into the learning rate. So we're going to do 30 iterations where we ease in. We're going to log every 10 steps. We're going to evaluate every 10. We're going to evaluate every 10 steps, and we're going to log every 10 steps. And we're going to evaluate every 25 steps. We're going to start our learning rate at the Karpathy constant because it's a big meme. We're going to use cosine learning rate, and we're going to be sure to add these. We are adding this information for the model. So the TRL library doesn't have to do extra work. That's why we built those prompts that we saw earlier that had all the special tokens in it. This is so we can set this to false. Then we have this max seq length thing. Max seq length is going to artificially limit the maximum sequence length. And then we use packing equals true because you'll notice, I'm not gonna scroll all the way back up just because I don't want to make anyone nauseous. But the idea is that we put the end of text token. So there's no need to have each example be its own example. We can pack a bunch into the context window. So let's say each example takes up 100 tokens. We have a max sequence length of 1,000. It'll fit 10 in there, no problem, right? So this is the idea of packing. Show it many examples at a time, let it learn all of them at once, instead of inefficiently only showing it one example at a time. And then we set up our SFT trainer with our model, our config, our tokenizer, the create prompt function we did. the training args we just set up, our data set. This is all the stuff we did at the top of the notebook just for the payoff here. And then we click dot train, and then it trains. And then we can look at, how it did. And we're going to ask a question about if this is overfitting, underfitting, neither, if so, why, and if so, how would you potentially mitigate these issues? And then we're going to share the model, which is the most fun part. You're going to put in your own addresses here. These cells will result in failure if you aren't a member of our organization, which you aren't. So please substitute your own address here, your own Hugging Face username, and then repo ID. And then we can compare the outputs finally. And what we see is we get, let's go to the mall together, have fun. We winds up being, they want to hit the mall with me and vibe out. We're definitely closer, right? We have this inclusion of additional language. We'll have so much fun together. And then we have my phone storage full because all the photos and videos. My phone storage is hella full because of all these pics and vids. And we get our phone storage maxed out with all these pics and vids. So we're on the right path with the fine tuning. It's looking a little bit more like the desired language, which is slightly less over Gen Z-ified. Okay, and with that, and then we can also see it on just whatever prompt we want. So you can put whatever you want in the box, and it's going to generate that. So what is the meaning of life? Universe to everything becomes what's the T on the meaning of life, the cosmos, and everything. Very Gen Z of it. And with that, I'll pass you guys back to Greg to get us breaker rooms.
What is the T on the meaning of life? Indeed. Did you guys catch all that? LOL. That was a lot. We understand. And one of the things that you might get asked in an interview is like, what is LoRA? What is fine-tuning? One way you can break it down is you could say, well, fine-tuning is all about modifying LLM behavior by updating the parameters or the weights. We like to do that in a parameter efficient way by fine-tuning with fewer parameters than the full fine-tuning of all of the weights. The most efficient and most typical way that we do this is with LoRA, low rank adaptation, where we fine-tune through a factorized matrix adapter approach. So when we're doing a parameter efficient fine-tuning through low rank adaptation, we're modifying behavior by updating fewer parameters through these factorized matrix adapters. So we can get savings. Savings, as the QLoRA paper will show you, from 780 gigs of GPU memory required, to like 148 gig GPU. Dope. Also, if you want to look at NF4 and double quant and that kind of thing, QLoRA paper is great for that. So we also do this quantization piece where we represent high precision numbers with low precision. And so thus we have PEFT-QLoRA fine-tuning where we modify behavior, the way the LLM acts, by updating fewer quantized parameters using this factorized matrix approach. In the end, we're talking about quantized LoRA. We loaded it into the GPU in a quantized form. We're doing LoRA, thus it's QLoRA. So we're going to give you guys about 15 minutes and then we'll come back and we'll close up. This is a big notebook. Okay, you're not going to finish this in class, but this is really where you get to start leveraging the GPUs. This is really where you get to start feeling like you're doing LLM engineering. And this is really where the rubber hits the road. So it's going to take you a while to get to the bottom of this. We're going to pick up right here in all the future classes, and we're going to keep accelerating. So take what you can from this, discuss it with your group, maybe make some time to discuss it further with peer supporters or other group members so you feel like you can really grok this. 15 minutes. We'll see you back to close out class. Time to wrap up, everybody. Hope you had a great breakout room with your groups. And in conclusion today, we saw that GPT, they were like, yo, SFT, it's pretty great, supervised fine-tuning. Whereas GPT-2, 3, they're like, well, maybe we don't need this so much. Turns out Instruct GPT and actually generally training these things to be better at instruction following does need supervised fine-tuning. And in fact, that's something that we'll pick up the thread of next time as we get into what else we need to do better in order to follow human instructions better. More human feedback. This is where we get into reinforcement learning. That's what's coming up next time with alignment. We can see that we can fine tune for tasks, for constraining the input-output schema, for specific language training. Quantization is important, parameter efficient fine tuning, quantization, low rank adaptation. These are all things that allow us to do more with less. That's a good thing for builders.